Dear students, welcome to the course Testing of Fibers and Yarns. Testing of Fibers and Yarns, and we are discussing about the measurement of the fiber strength and its measurement. Okay, in the last class I have discussed about the different principles like constant rate of loading, constant rate of elongation, constant rate of traverse for the measurement of the tensile strength of the fibers, yarns or fabrics. Okay, so we have seen in detail about those three principles. Okay, so coming to the today's class, where I am going to discuss about the strength, that is how to measure the single fiber strength. How to measure the fiber strength by using this Instron Tensile Strength Tester. By using this Instron Tensile Strength Tester, which works on the principle of strain gauge principle. Okay, so by using this instrument, we can say that one of the advanced instrument where to measure the fiber strength, in the sense that's not an easy job. Why? Because the fiber is very small, very short. Okay, so 1.5 to like 1.52 inches length. So where the instrument which we are using to measure the fiber strength, that should be of very precise, and that should be of very intricate, like this thing. So this Instron, by using this Instron, where we can measure the fiber strength, single fiber strength. Okay. Now, if you look at this instrument, so which operates on bundle wire type strain gauge principle. So which works on this strain gauge principle, and it consists of the interchangeable load cells that contains the strain gauge. So interchangeable load cells, that load cell, it consists of this strain gauges. Okay, if you look at a strain gauge, so it is a kind of a sensor which resistance varies with applied load or applied force. So when the force is applied, obviously what will happen? The resistance of this strain gauge is going to vary. Okay, understand? So strain gauge is a sensor whose resistance varies with applied force. So if the force applied is high, obviously the resistance also it varies, and it converts the force, pressure or tension or weight, etc. into a change in the change in electrical resistance, which can be measured. So whatever this resistance which is varying with respect to application of force. Okay, application of force, the resistance of this strain gauge is going to vary. Okay, so it converts the force, pressure or tension or weight, etc. into a change in electrical resistance, which then can be measured. Okay, so change in electrical resistance, that may be due to force, pressure or tension, and that can be measured. Okay, and now you can see here, this is the strain gauge. This is the image of strain gauge. Okay. Now, so it is a versatile instrument. It is a versatile instrument which is used to measure the loads from 2 grams to 100 kgs. Which is used to measure 2 grams to 100 kgs, and the load cells are located centrally in the fixed top head of the instrument. So where whatever it may be, the tensile strength instruments are there where it needs the presence of load cell. Okay, here where the load cells are the load which is varies from 2 grams to 100 grams, and the load cell which is located centrally in the fixed top of the instrument. Now you can see here, so this is the Instron Tensile Strength Tester. You can see this image, and here you can see, so this part is nothing but the load cell, and this load cell, it measures the load and then it is processed and it is connected to the display. Understand? And if you look at the principle, so this Instron Tensile Strength Tester, it works on the strain gauge principle. Okay, now we will discuss what is the strain gauge principle and how it is used in measuring, or how it is used in measuring the deflections in the load, that is according to the force applied, how the resistance of these wires are going to changes, and how it is then converted into the required parameter. Okay, now if you look at this strain gauge principle, okay, now you can see here, for example, so this is a beam, that is, this is a cantilever beam, that is one end of the beam is fixed, and now you can see, so this is the beam and one end of the beam is fixed, and which makes it as a cantilever beam. And now you can see here, so this is A, B, C and D. Now, so this, the end of beam, that is BC, is connected to the J1, that is jar. So I told you now, in tensile strength measurements, we have to mount the specimen in between two jars, that is J1 and J2 are the two jars. In between the jars, we have mounted this specimen. And this specimen, the bottom jar is connected to a suitable screw type mechanism for maintaining, that is for imparting the extension in the specimen. Now, so this J1 and J2 are the two jars, and the specimen is clamped in between these two jars, and the top jar J1 is connected to this beam. So this is the actual thing. Okay, now, and top of the beam, where we kept a resistance wire R. The top of the beam we have mounted a resistance wire R. Now think that there is no load applied. Now what will happen? The beam will not get deflected and there is no change in the resistance of the resistant wire. Now if you look at this image, now what is happening here? Where the load measuring mechanism, it is making the bottom jar to move, thereby it imparts the specimen to elongate. Here you can see the specimen is elongating, and this top jar is connected to this beam, is it right? Top jar is connected to this beam, cantilever beam, that is the end is BC. Now what will happen? Whenever the specimen started elongating, obviously the beam also starts elongating. Now you can see here. So it also starts deflected. The beam is deflected. Now what will happen at the time of beam deflection, where the AB, that is, it is going to be, the top surface of the beam is going to extend, whereas the bottom of the beam, that is CD, is going to contract. Obviously it is extending like this. The bottom portion is going to contract, the top of the beam is going to extend. Now we have mounted this resistant wire R on top of this AB. So that what will happen? If AB length is extending, obviously the resistant wire R is also going to extend. So thereby, where there is a change in the resistance of the wire. So depending upon the load which is applied, where the resistance of the resistance wire is going to changes. So the load is proportional to the resistance, change in the resistance. So this is connected to suitable processing unit, and then we are getting the braking load unknown. Understand? So this is what this strain gauge principle is. Okay. Now, if you see this, when the beam bends, the length of upper face, that is AB, that is, here you can see that is increases, and the lower face, that is CD, obviously it is decreases. And you can see the NL, that is the center line, which remains unchanged. So there won't be any change in the central line. And the resistance wire R, which is centered at AB, also expands, and thus the value of resistance changes. So whenever you are increasing the load, the resistance value of the wire is going to changes. If there is no load, there is no change in the resistance of the wire. Okay, and convert this value of the change in resistance to load values. Load values which is applied on the specimen. So this change in resistance is going to be converted into its breaking load or the load values. Okay. Now the two resistance wires are placed on upper and the other two are on the lower surface, and it form a kind of Wheatstone bridge. So, and it forms a Wheatstone bridge. Okay, now you can see the two resistance wires are placed on the upper and the two resistance wires are placed on the lower surface. Two resistant wires, and finally it forms this Wheatstone bridge. Now you can see here. So in this image, CD is there now. So this C, in this image you can see C and D. So this is one end of the beam. Is it right? You can see one end of the beam, C and D. So C and D, CD is connected to the load, that is the jaw. Now what will happen whenever the bottom jaw moves downwards? Obviously there is a deflection in the CD. So whatever this output, this is the input. Okay, this is the input. Okay, now, so you can see, so you can see in this image, so this is AB and this is CD. Now what is happening? Whenever this AB extends, listen carefully, whenever this AB extends, then only there will be some change in the resistance values. Understand? So now you can see here, so this is the Wheatstone bridge, where this is A and this is B. So this is the input. So whenever there is a change, or whenever we are imparting load on the beam, load on the specimen, that is extending the specimen, obviously the end of beam, that is AB, top surface of the beam is going to expand, that is it is going to extend. Obviously there will be some voltage, and based on this, that is there will be some resistance change, and finally we are going to get some output. When we are going to get the output? When there is a change in the resistance of the resistant wire. So whatever the applied voltage we are giving, the input voltage, whenever there is a change in resistant value, so where we are getting the output. If there is no change in the resistance value, and there is no output. So when the resistance is going to change, obviously when the bottom jaw is moving downwards, where the specimen is extending, and the top jaw, it will extend, that it will pull the beam to deflect, so that the AB is going to, that is expand. Since AB is expanding, on top of which we have mounted our resistance wire, that is strain gauge. So obviously there will be some change in the resistance, and this change in resistance will give the output voltage. And this is taken out and this is processed, and finally we are getting the load values. Okay, and with the beam undeflected, as I told you already, with the beam undeflected, no voltage across CD. There won't be any voltage across CD. When a voltage is applied across AB, the bridge is balanced. Even though if you are providing the voltage at AB, that is input voltage, so there won't be any output, then we can say that the bridge is balanced. The bridge is balanced. Okay. Now, when the load is applied, what is happening? Obviously, the deflection occurs on AB, that is top surface of the beam, and the values of the resistance changes. That is, the R is also deflecting now. So, the value of the resistance change, and a voltage is produced across CD. Obviously, the voltage will produce, that is, which is proportional to the applied load. If the applied load is more, where the voltage, whatever the voltage we are getting at output at, is going to be high. And if you look at some of the advantages like It's free from inertia, errors and friction, that is beginning. Beginning sometimes what will happen is where without start doing the testing itself, where there might be some the tension which is applied on the specimen which causes these readings to be varied. So that sort of problems are not there, and the deflection of end of the beam is very small. It is not like whatever the thing which is shown in the image, like complete deflection. Very, very small deflection, and thus it is tested under CRE conditions. It is constant rate of elongation condition. Okay. And versatility is the type of instrument is we can find out the tensile strength of yarns, fiber, fabrics at wide speed ranges. It is not that it is only meant for fiber testing. It can be used to find out the strength of fibers, yarns, and then even fabrics also. Okay. And if you look at disadvantages, like it is a costlier instrument and it needs the person who is working, he needs some kind of expertise. Okay. And if you look at this instrument, the Instron Tensile Strength Tester, so whatever the jaws are there, like upper jaw and then bottom jaw, the upper jaw is suspended from the cell through a coupling. You can see here, this is the upper jaw. Okay, all these grippings are pneumatic grippings. Okay, and the lower jaw is mounted on a suitable screw-driven mechanism. Here, bottom, there is a screw-driven mechanism, so which makes the bottom jaw to move at constant rate of elongation. Okay, and there are gears to change the speed of the crosshead, that is, which makes the bottom head to move. That is, change in the rate of extension of the specimen. So we can change the rate of extension in the specimen varies from 0.02 to 50 inches per minute. So we can adjust the rate of extension of the specimen also. Okay, and on the bottom of the instrument we have the control switches, so which are govern the movement of the crosshead. Okay, and the load cell output is set to control electronic circuit and the pen recording equipment. And whatever the load cell bottom to that load cell, you can see here where the bottom jaw, that is top jaw, is attached. So whatever the load which is taking, that the load is required to break the specimen, where here in the load cell we have the strain gauges, since the specimen is extending, which is causing the change in resistance of the strain gauge which is there in the load cells, and thereby where the resistance value changes and then the voltage also which is generated, and then that is going to be converted into a suitable that is converted into load. Okay. The load cell contains a metal beam in the form of a cantilever. So this is what I am telling, and whatever the strain gauge principle we have discussed, the same thing. Okay, so the load cell contains a metal beam in the form of a cantilever. So one end of the beam is fixed and the other end is free to move. And the strain gauges consisting of a grid of very fine wire are bonded to the surface of the beam. So whatever the strain gauges are there, which is consisting of a small grid of very fine wire, strain gauges of very fine wire are bonded to the surface of the beam. So on the surface of the beam, the strain gauges are going to be bonded. Now, thus the true strain gauges are used, and these are connected in the form of a Wheatstone bridge. I have shown you like the connected in the form of a Wheatstone bridge. How Wheatstone bridge is going to be? Okay. So this is how the Wheatstone bridge is going to be. Okay, so here we are giving the input and here we are getting the output, like our output voltage. So this is the Wheatstone bridge. So whatever the strain gauges which consist of a very fine wire are bonded on the surface of the beam, metallic beam. Now the strain gauges are used and these are connected in the form of a Wheatstone bridge, like this. Okay, now, so each strain gauge has a normal resistance of 120 ohms. Normal resistance of 120 ohms. Okay. And the Wheatstone bridge network of strain gauge is excited from an oscillator of frequency 355 cycles per second. And the specimen changes the resistance balance of the Wheatstone bridge and the signal is amplified by a circuit. And when the resistance value of this balance of, that is Wheatstone bridge, it is going to change, or when this Wheatstone bridge is going to imbalance, when there is a change in resistance of these wires. When the wire resistance is going to change, whenever the beam is going to deflect. And obviously the beam is going to deflect on par with the specimen extension. Okay. And the signals operate the pen recorder on a chart to trace the load elongation curves. The load elongation curves. So finally, from this we are going to get the load elongation curves, and apart from this we are going to get the breaking load and breaking elongation. Understand? So this is about the Instron Tensile Strength Tester, which works on the strain gauge principle. Understand? Hope you understand this class, where by using this instrument we are finding out the strength of single yarn, single fiber yarn, and then fabrics also. It is a versatile instrument. Understand? Hope you enjoyed this class, and we will meet in the next class and we will discuss about this bundle fiber strength. So this instrument, it is a costlier instrument. Okay, so it is not possible for the spinning industries to have this instrument. So where they need to measure the bundle fiber strength. So they can measure the bundle fiber strength, and that will give them an idea about what is the strength of fiber they are having, and based on that they will be taking care of the rest of the things. And this bundle fiber strength, it can be measured, it can be done by using this high volume instrument, Understand? So that is an automated version, and apart from that high volume instrument, we have an instrument called stellometer, which is a manual. That is, it's not an automated machine. It is a manual kind of machine, so which can be used to carry out the bundle fiber strength manually. So about this instrument we will discuss in the next class. So till then, thank you. Bye.